So we're going to get started. So we don't have any projector in the room, so everyone's going to be on Zoom wherever you are. And of course, as always, I'll record it and put it up on YouTube. So we'll be all set with that. All right, so we're going to finish up optimization. Wow, this is going to be weird. We're going to finish up optimization today, and then we're going to change gears dramatically and talk about numerical integration. So we're going to do one more example of a simplex problem. We'll work through our uber long word problem here, and we'll formulate it, put it into standard form, and then find the solution, determine the solution. Then we'll talk a little bit, just kind of debrief about simplex method, how it works as an algorithm, and so forth. And then we'll move on to numerical integration, which will be lots of fun, I hope. Okay, so let's get started here. So here is the problem. So we have raw material coming in to a manufacturing plant, 77 tons is delivered each week, and these are metric tons. A TONNE is a metric ton as opposed to an English ton, which is 2,000 pounds. So metric ton is 1,000 kilograms, which is not the same. The plant has the ability to produce two different products from this raw material that each require different amounts of raw material, amounts of time to produce, and have different on-site storage requirements. And then finally, they each produce a different amount of profit. So I've pulled all the information together. For product A, it requires 7 tons of raw material to produce one of product A. It takes 10 hours per ton to produce. The plant can only store up to 9 tons per week of product A, and the profit per ton is 150 of product A. And then the parallel numbers for product B are 11 tons of raw material to make one of product B, 8 hours per ton to make one of those product Bs, but the plant can only store up to 6 tons per week, and then the profit is 175 per ton. In addition, we can only work on one product at a time, and we can run the plant for 80 hours per week. So 80 hours per week, basically 2 cycles of, what do we call it? Shifts, 2 shifts of people working in the plant. So 80 hours per week, one product at a time. And we want to determine how much of each product to make, X1 and X2, that will maximize the profits. All right, so that's the big uber problem statement. All right, so we have 2 variables, X1 and X2. These are design variables. X1 is the tons of product A that's produced each week. X2 is the tons of product B produced each week. Now here's where you have a little bit of a decision to make. When you read that word problem, you could easily imagine saying, well, let me have my design variables be the number of widgets A and the number of widgets B. Instead, we're going to say the number of tons of product A and the number of tons of product B. You can do it either way. You'll get the same answer in the end, but I've decided to do it this way, and we'll see how this works out. Okay, so 2 design variables, capital N is equal to 2. And I just start wherever it makes sense. So sometimes I start with the objective function. Sometimes I start, as I did with the train example, with the positivity constraints. So wherever it makes sense to start, to kind of get yourself going and get some of this information in the word problem into equation form, just go ahead and do it. It doesn't matter the order. Don't worry about the order. But in terms of the objective function, the objective is to make as much money off of these widgets as possible. So back here, remember that the profit is 150 per ton for A and 175 per ton for product B. So 150 times X1 plus 175 times X2, that would give us the total profit, we'll call it J bar, that we make each week. And that's what we want to maximize. Oh, we're back. And we didn't do anything. Great. So interesting. Oh, we waited for you to leave and then we plugged the wire back in and now everything's fine. No, I'm just kidding. Just kidding. Just kidding. You guys are cruel to each other playing these little jokes. All right. So that is the cost functional, which is the maximum. That's the profit. That's the amount of money we want to maximize that. Now, there's, of course, a bunch of constraints. So again, just work your way through the problem step by step. Don't worry about the order in which you put down these constraints. You can always start with the positivity constraints because you think, okay, wait, I'm making stuff. I can't have negative tons of A and negative tons of B. Fine, so x1 is greater than or equal to 0, x2 is greater than or equal to 0. If you want to start there, that's fine. I have it last. You can start wherever you want. So I've decided to start here in terms of constraints with the total raw material. So the limit is 77 because that's how much is brought into the plant each week. How much I use is 7 tons for A and 11 tons for B. So 7 times x1 plus 11 times x2 has to be less than that 77. Okay, so 7x1 plus 11x2 is less than or equal to 77. Inequality constraint. Then I have my 80 hours per week constraint. So the amount of time it takes to make 1 and the amount of time it takes to make 2, when I add up the number of hours times the time, number of hours times the tons, times number of hours times the tons, has to be less than 80. So that is right here, 10 hours per ton, 8 hours per ton. So 10 times x1 plus 8 times x2 has to be less than or equal to 80. Finally, we have the limit of 9 tons or 6 tons per week that we can store on site. So x1 has to be less than or equal to 9, and x2 has to be less than or equal to 6. All right. And then again, finally, the positivity constraints, x1 and x2 both have to be positive. So I have my objective function, which is the maximum profit. That's the profit to maximize. I have the constraint related to the amount of the tons of material. I have the constraint on the time, and I have constraints because of storage, and then I have my positivity constraints. The hardest part is setting up these equations. Once you set up the equations, the rest of it is basically plug and chug. It's basically just follow the steps, do the steps, and get the answer. If you do this wrong, obviously the rest is going to go haywire. But so in other words, the reason why I say that is when I do a problem, any problem, I always have these portions of the problem where I purposefully, intentionally slow down. So there's parts where you kind of just turn your brain off, thinking about other things, and you do it. You can do it with your hands tied behind your back and your eyes closed. And then there's other parts where you just, okay, wait, I need to slow down, take my time, and make sure I get this portion correct, because if I don't, then the rest is going to be a mess. So this is the part, translating the word problem into these equations and constraints, that I need to really slow down and make sure I've got everything accounted for. So in terms of a optimization problem, now just go back, read the entire problem statement again, and make sure that every piece of it's been taken into account. So yeah, I've taken into account the 77 tons. I've taken into account the amount of raw material to make each of them, how long it takes to make each of them, the amount of storage, and the amount of money that I make per ton, as well as the 80 hours per week. So just literally just check them off and make sure that everything has been accounted for in your statement. So now I have one objective function. I actually have 0 equality constraints, and I have 1, 2, 3, 4 inequality constraints. plus my 2 positivity constraints. So what's capital N? Anybody? Capital N is the number of design variables. So in this case, that is I think I actually just said it a moment ago. So capital N is the number of X variables. It's just 2, right? What is M? M as in Mary. Remember, M is the number of equality constraints, which in this case is 0. And then S is the number of inequality constraints. 1, 2, 3, 4. So N is 2, the number of X variables. M is 0, the number of equality constraints. And S is 4, the number of inequality constraints. So you can write that down. N is equal to, M is equal to, S is equal to, and you can use those numbers to help along the way later on. Okay, then the next step, so you take the word problem, put it into a set of equations. Then the next step is to put those equations into standard form. So remember all the components of standard form. The first thing is that the objective function has to be posed as a minimization problem. In this case, it's posed as a maximization problem. So that's why I called it J bar. And now I'm going to rewrite my objective function J as minus J bar. So that's minus 150x1 minus 175x2. So I'm maximizing the profit, J bar, which is equivalent to minimizing J. Okay, so I just multiply through by a negative sign, -1, and I change it from a maximization to minimization. Okay, fine, that's done. The second thing I have to do is be sure that all of my inequalities are less than or equal to's. And they are less than or equal to, less than or equal to, less than or equal to, less than or equal to. So I don't have to do anything with that. The next thing I need to do is change all of my inequality constraints into equality constraints. And I do that using slack variables. So we had that 7x1 plus 11x2 is less than or equal to 77. We can make that an equality constraint by including our first slack variable S1. And remember what it does. It just takes up the slack so that we can make this, instead of a less than or equal to, we can make it an equal to sign. So S1 has to be positive, sorry, it has to be non-negative. It could be 0. If 7x1 plus 11x2 is equal to 77, then S1, of course, would be 0. Or it could be positive in the case where 7x1 plus 11x2 is something less than 77, then S1 takes up the slack, the difference between those two. Same thing for the second inequality constraint. We had 10x1 plus 8x2 is less than or equal to 80. Add in another slack variable plus S2. That takes up the slack between the left side and the right side of the inequality in order to make it an equal sign. X1 has to be less than or equal to 9. So to take up the slack, we incorporate an S3. X2 has to be less than or equal to 6. So to take up the slack, we introduce S4. So it's that easy. Does everybody understand slack variables? So we discussed it, I described it, I motivated, I kind of went through an argument for motivating why we introduce them in the way that we do. Once we understand that, I just simply add them in. And the only way that this works, the way we incorporated our slack variables, is if, again, all of our inequality constraints were less than or equal to. If they're greater than or equal to, then my slack variable is incorrect. So that's why we make them all less than or equal to first, and then introduce the slack variables. Okay, so now my 1, 2, 3, 4 Inequality constraints have been converted to equality constraints. And then we also have our additional, did I write them someplace? I'm sure I did somewhere. But then I also have the positivity constraints on the slack variables. All right. So once again, we said this just a moment ago, but n is equal to 2, that's number of design variables, m is equal to 0, number of equality constraints, and s is equal to 4, the number of inequality constraints in the original problem. Those numbers do not change. Even though I've converted my inequality constraints into equality constraints, I don't move my s's to m's. S is still equal to 4, m is still equal to 0. Now, in terms of remember the basic and non-basic sets that we discussed last time, that is determined by how many variables are in the non-basic set is determined by n minus m. So the number of design variables, in this case 2, minus the number of equality constraints, in this case 0, so that's equal to 2. That's the number of variables that's in the non-basic set. Remember, the non-basic set are the number of variables that are going to be equal to 0 at each vertex. So at a potential basic feasible solution, the number of the variables that's equal to 0 will always be 2. And we'll see that as we go through the problem. The remaining 4 variables are going to be in the basic set. So there's a total of 6, 2 plus 0 plus 4, so that's 6. 2 of them will be 0, and 4 of them will be non-zero. And therefore 2 in the non-basic set and 4 in the basic set. Okay, let's draw the feasible space. Remember, the feasible space only has to do with the constraints, not the objective function, only the constraints. So let's walk through how this is going to look. So this is x2, and this is x1. And I'm going to go out here to have to go to 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11. And then here, I'm going to go up to 10. So this is 0, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we can draw it because we only have 2 design variables. If n is more than 2, then I can't draw it. But if n is 2, then I can draw it. All right, so let's walk through. And you can look at this form of the constraints, or you can look at this form of the constraints. So let's start with the positivity constraints. x1 is positive and x2 is positive. So that means that x1 is equal to 0 is the x2 axis, and x2 is equal to 0 is the x1 axis. So it has to be somewhere to the right and up. So somewhere in the first quadrant of the x1, x2 space. Okay, let's go back here. I can pick any of the other ones. Let's start with these because these are easy. x1 has to be less than or equal to 9. And x2 has to be less than or equal to 6. So x1 has to be less than or equal to 9. And x2, 1, 2, 3, 4, 5, 6, has to be less than or equal to 6. So this is 5 and 1, 2, 3, 4, 5. Okay. So this line corresponds to actually S3 is equal to 0. I'll get to that in a second. And this one corresponds to S4 is equal to 0. So if I go back to this form, x1 is less than 9. If x1 is equal to 9, then that means S3 is equal to 0. Are we confused yet? So this line corresponds to S3 is equal to 0. So it has to be to the left of that because it has to be less than or equal to that. Then this one, x2 is less than or equal to 6. If x2 is equal to 6, then S4 is equal to 0. x4 is equal to 0 when x2 is equal to 6. So it has to be below. Okay, this is fun. Well, at least I'm having fun. All right, now we have 2 more. So we did the positivity constraints. Boom, boom. We did these 2. Now we need to do this one and this one. So the easiest way to look at these 2 right here, let's look at the first one. It says 7x1 plus 11x2 is less than or equal to 77, or plus S1 is equal to 77. Just forget about the S's. Let's just set them equal to 0. And I want to draw the line that corresponds then to S1 is equal to 0 and S2 is equal to 0. Well, this is an equation of a straight line. If I set x1 to 0, then I have 11x2 is equal to 77, which would mean that x2 is equal to 7. So if x1 is 0, x2 is 7. If x1 is 0, x2 is 7, which is right here. I'll draw the line in a second. Then if x2 is 0, then this term goes away, and I have 7x1 is equal to 77. So that would mean that x1 is equal to 10. So when x2 is 0, that's, whoops, that is this x1 axis. And what did I say it's equal to? It's equal to 10. So it's right here. So I need a straight line, straight-ish line that goes between those 2 points. So that corresponds to S2 is equal to 0. Oh, sorry, S1. Wait, it was 11, no? Did I get it wrong? Yeah, it's 11. Nah. This is right. My bad. Yeah, so it goes to 11 here. X1 is equal to 11. So I go boop-a-doop-a-doop-a-doop. That is corresponding to S1 is equal to 0. And it has to be below. It's less than or equal to. So it's somewhere below that line. So you can see that every time I add one of these, I'm restricting the feasible space. The feasible space is getting smaller. With the positivity constraints, the feasible space was anywhere in the first quadrant. Then I incorporated these 2 constraints, and then my feasible space is this rectangle. And now I incorporate this constraint, and now I've got this shape right here. So far, that's my feasible space. But I still have one more. And that's this second one here. So 10x1 plus 8x2 is equal to 80. So if x1 is 0, then x2 is equal to 10. x2 is equal to 10, so it's way up here. And then if x2 is equal to 0, then 10x1 is 80, so x1 is 8. So that is right here at 8. So now I have my straight line going like that. So that corresponds to S2 is equal to 0. And once again, it has to be less than or equal to, so that's there. So once again, we have further restricted our feasible space. It's now this. Let me define the corners. I'm going to call this A, B, C will be this point where they intersect, D, where these two intersect, and then E. Oops. So as I go from A to B to C to D to E back to A, that's my feasible space. Yeah. Exactly. So the arrows on this arrow right here is saying that x2 has to be positive, and this arrow right here is saying that x1 has to be positive. Exactly. Okay, so each line corresponds to one of my constraints, and when I incorporate all the constraints, I better have a closed polygon. If it's not closed, then when I tip my table, the marbles could spill out and they could go to negative infinity. So I want my constraints, if it's a well-posed problem, I want the constraints to be such that they form a closed polygon in the x1, x2 space. So that however it's tilted, the minimum is always going to be one of those vertices, either A, B, C, D, or E. Awesome. Any more questions about that? This is kind of the point where you're like, oh, okay, it looks like I may have actually formulated this correctly. Or at least I haven't formulated it wrong, because it is a closed space. It all makes some sense. You will notice that the S3 is equal to 0 constraint is actually redundant. It doesn't in any way restrict the feasible space because this one has moved it over. So this turns out to, now just graphically you can tell that S3 will never be equal to 0. It'll always be something positive. All right, but again, you can see that it's a closed polygon. That's exactly what we want. We now kind of have a game plan, a map of the possible basic feasible solutions, A, B, C, D, and E, that are potential solutions. We just need to find the one that gives the maximum, or well, the minimum, which corresponds to the maximum profit. Okay, so I've listed those in the table here, the 5 points, basic feasible points. And I've indicated for each of them which 2 variables are 0. So in other words, which 2 variables are in the non-basic set. So for A, that corresponds to x2 and x1 being 0. So x2 and x1. B, that's right here, that corresponds to when x2 is equal to 0 and s2 is equal to 0. So x2, s2. C corresponds to, that's this point right here, so that corresponds to when s1 and s2 are equal to 0. S1 and s2. D is when S1 and S4 are equal to 0. S1 and S4. E is when X1 and S4 are equal to 0. X1 and S4. So again, there's 2, and you don't have to do this table. I'm just doing it just to kind of map out where things are going to go and what the possibilities are. It's not necessary, but it just helps me to say, okay, yeah, I can see which 2 variables are going to be 0, and therefore in the non-basic set for each of these 2 situations. Sorry, for each of these 5 points. Then the Simplex Tableau, here it is in matrix form. So here's all my variables. Start with the variables. I have J, that's the objective function. I have my 2 design variables and my 4 slack variables, all just listed in order: J, X1, X2, then S1, S2, S3, S4. Then I just look back here at 641 and 642. And I'm just going to write down each of these equations in this matrix form. So the first equation says that 1 times J plus 150 times X1 plus 175 times X2. And remember that you always have 0 coefficients for the slack variables in the objective function. So it's just 0, 0, 0, 0. And that's equal to 0. So that came from J was equal to minus 150 X1 minus a 175 X2. And all I've done is write it into this matrix form. So obviously I brought these over to the other side so that all the variables are on the left. 1 times J, that's from here. 150 times, it's supposed to be an X1. 150 times X1, that's here. 175 times X2, 175 times X2, and it's equal to 0. Great. So that's the objective function. And then I have 4 equations that came from my equality constraint, well, what were originally inequality constraints that I converted to equality constraints. These are always going to be 0 because J does not appear in the constraints at all. So the first column is going to be all zeros except for the 1 in the first slot. Then I have 7 times X1 plus 11 times X2 plus 1 times S1 is equal to 77. That should sound familiar. That's this equation right here. Then the next one, 10x1 plus 8x2 plus S2 is equal to 80. You have 0 times J plus 10x1 plus 8x2 plus 0 times S1 plus 1 times S2 plus 0 times S3 plus 0 times S4 is equal to 80. And then the last two, I have X1 plus S3 is 9. So 1 times X1 plus 1 times S3 is equal to 9. And then finally, 1 times X2 plus 1 times S4 is equal to 6. Does that make sense? Just converting those same equations in standard form into, yep, thanks. So converting them into the matrix form. And now, again, there's a check you can make here. So along the way, you can make all these checks to make sure everything sort of kind of makes sense. So you think, okay, how many equations should I have? And how many variables, how many columns should I have? So how many rows and how many columns? Well, I should have a row for each of my objective functions, which I have 1, and my constraint equations, for which I have 4. So I should have 5. 1, 2, 3, 4, 5. Great. Then the number of columns should be the number of total variables, the total number of variables. I have J, I have the design variables, X1 and X2, and then I have the slack variables, S1, S2, S3, S4. So I should have 6. 1, 2, 3, 4, 5, whoops, 7, like I said, 7. Oops. J plus X2 plus the S's, S1, 2, 3, and 4, I should have 7. So that makes sense. And it should always be underdetermined. Remember, it should always be underdetermined. The number of rows should always be less than the number of columns. If it's the same, then there's a unique solution and there's no optimization necessary. If you have more equations than unknowns, then you have an overdetermined system. And once again, there's nothing to optimize. In fact, there is no solution. So we want a case that has actually an infinity of solutions, so there's room for optimization. So an underdetermined system has that flexibility to optimize it. Okay, now what I can do is, in the previous example, the train car example, we only had 2 points, A and B, that were potential optimal solutions. Now I have 5. I could go through and calculate the J for each of these 5 points from this Simplex Tableau and look at them and see which one is the smallest, which corresponds to the maximum profit. I could do that. And if I only had 2, that's fine. I'm patient enough to do that. But I don't have the patience to do that for 5 points. So I'm going to be a little bit more methodical, a little bit more like how the simplex algorithm actually works. So, but just take point A as an example. For point A, 2 of the variables are 0. In that case, look at my table, it's x1 and x2. What are x1 and x2? Well, that's the number of tons of product A and B that I've made. If those are both 2, that means I haven't made any. So I sure hope, and my boss certainly hopes, that that is not the optimal solution. So at point A, x1 is 0, x2 is 0, and the profit would be 0, because J, which is 150 times x1 plus 175 times x2, well, that would be 0. So I have 0 profit. So I'm going to start there at that point, even though I know it's not the optimal solution. We'll start at A when x1 and x2 are 0, and J is also then 0. Now, remember what we're trying to do. As I go from point to point, I want the value of J to decrease. So I'm going to go either from A to B or A to E. I'm going to go from A to B, and let's see if it actually decreases. So at point B, x2 and s2 are 0, x2 and s2 are 0. So at point B, I can determine that J is equal to minus 1200. Now you think, wait, I'm trying to maximize profit. Well, yeah, remember, J is the negative of the profit. So this is negative profit. So actually, the larger the magnitude of the, or let me say it this way, the more negative the J is, the better. Because the more negative the J is, the more positive J bar is, and that's maximizing the profit. Okay, so it's going in the right direction. I've decreased J from 0 to minus 1200. If I go to point C, so let's look back here. I went from A to B, and I'm going to go to C. So that's this point right here. That's when S2 and S1 are both equal to 0. If S1 and S2 are both equal to 0, then that corresponds to J being minus 1,413 and 89. So good, it's getting smaller. So C is better than B. It makes me happy. And then I would go to D. And I'd figure out what J is, and I'd find that actually J starts to then increase. So if I were to go to D, J would start to increase. So then that tells me that C is the optimal solution. Now you might ask, wait. I arbitrarily chose to start at A, and I somewhat arbitrarily chose to go to B instead of to E. So I'm going counterclockwise instead of counterclockwise. Or sorry, I'm going counterclockwise instead of clockwise. Without checking E, how do I know that that's not the minimum? Well, that's because this is a linear programming problem. So remember what we said about these feasible spaces. I have my feasible space. Any point in here, in this region, feasibly could be an optimal solution. However, I know because it's a linear programming problem, it has to be at one of the vertices. And the reason is, and this is the answer to my question of, well, why can't E be a minimum? Is because the lines of constant J are going to be, I don't know what they are, but they're going to be straight lines that slice through our feasible space. and j is either increasing or decreasing as you go from one line to the next. So in other words, if it increases from C to D, it can only increase from D to E. It can't decrease. So I don't actually have to check E, because if it's increasing from C to D, it's going to increase from D to E. That was, again, the basis for, okay, let's start at some random point. I chose A, and I went to B, and I saw it as decreasing. I'm like, okay, well, that's good. Let's keep going and see if it continues to decrease. So I go to C, and sure enough, it's decreasing more, but then it starts to increase to D. So it can't, it's, in other words, as I go around the boundary, you're not going to get a roller coaster. It can only be going down or up monotonically, down or monotonically up. And once it switches down, or in this case, switches up, it can't switch back to down again. No, there's only one dip in the roller coaster, so to speak. Okay, so we can stop at C, and that is the optimal solution. The maximum profit per week then is J bar, which is minus J, which is $1,413.89 quadrillion dollars. We were actually arguing in my family the other day. Is a bazillion bigger or a gazillion bigger? You would think a gazillion is bigger than a bazillion, right? Because G's are bigger than B's. So that's what we went with. Okay, well, that's the profit. Now, how many actual things, A and B, do we manufacture? Well, the values of X1 and X2 that correspond to this J are 4.89 and 3.89, and we get that from the solution. So when you zero out S1 and S2, so when you zero these out, you'll get the solution for X1, X2, as well as J, and S3 and S4. And the solution for X1 and X2, well, that's really what you're after. That's what you tell your boss. Make 4.89 of product A and make 3.89 of product B. And that will maximize your profit each week. Okay, any questions about that example? I know these are not easy. You do need to really slow down, as I keep saying. How do you get the numbers for J again? I'm getting all of these numbers from solving this system of equations. Now remember, as it is in this form right here, I can't solve it. I can only solve it if I have the same number of rows and columns. So that's why in this case, I have to have two of my columns get zeroed out. And that's because two of my variables, in this case, S1 and S2, that corresponds to these two, those columns are removed. And so now you have a 5 by 5 system of equations. You solve them, and you get all of these variables. You get J, X1, X2, S3, S4, S1 and S2, of course, are 0. So for each of these points, A, B, C, D, different pairs of these columns go away. So for A, X1 and X2 go away. For B, X2 and S2 go away. For C, which is the actual optimal point, S1 and S2 go away, and so forth through D and E. Does that make sense? So we convert our underdetermined problem into a problem that has a unique solution by imposing the fact that we know that in this case, two of the 7 variables are 0 at the basic feasible solution, at the optimal solution. Okay, any other questions about the process? We'll kind of debrief here through a couple slides of remarks. All right, simplex. Why do we call it a simplex? The simplex is actually a technical term. It is the simplest polygon or polyhedron. So the simplest polygon in 2D and the simplest polyhedron in 3D. The simplest polygon in 2D is a triangle. The simplest polyhedron in 3D is a tetrahedron. So that's where the term comes from. So it doesn't really have anything to do with the algorithm. That's just the name that someone decided to use. And a tableau, as I've said before, that's just a fancy Frenchie. So that's a Frenchie is a fancy French word for a table. So that's where the tableau comes from. The actual programs that do what we just did in an automated way for a wide range of problems are extremely complex. If you look at the codes, they're thousands and thousands, sometimes millions of lines long. The simplex method is somewhat simple conceptually. It's a little tedious to carry out, but it's actually not that difficult. Again, I keep doing my table with the bumpers on it. You know, so you have that image in your mind. It's like, okay, that all makes sense. And it's just a matter of, well, where do I start and how do I know which direction to go from one possible point to another? So these programs are extremely complex because they have to handle a whole host of different possibilities, which I'll discuss on the next slide. And so again, I focused on the principles behind it and not on the actual, there's no way I've given you anywhere near enough information to actually program this. It's just what I've given you is kind of a sketch of the procedure. So there's a bunch of additional questions. How do you choose the starting basic feasible solution to start your algorithm, which I haven't addressed at all. I just started with A because it's the first letter in the alphabet, which is a really dumb way to make that decision. So the first big decision is, how do you know where to start? And then as you go from point to point, how do you choose the next basic feasible solution? So do I go from A to B, or do I go from A to E? How do I make that decision? So that's the next big thing. And of course, that determines the associated leaving and entering variables that are coming into my non-basic set and leaving the non-basic set. So there's a lot of programming that goes into making those two decisions. Now, one thing that's intuitively obvious is a problem with the simplex method is, imagine I had a problem where I don't have 5 basic feasible solutions. Say I had 1,000. So I had 1,000 of these vertices, and I have to figure out where to start, which direction to go. If I can only go around the perimeter from one to the next, it could, if I choose the wrong one, I could end up going around a pretty long way. So there is another approach. It's called the interior point method, which allows it to zip across the feasible space. So it requires additional smarts, but it could say, well, for some reason, I think, well, if I start at A, rather than going to B and then to C, what if I just had some way of going directly to C? Well, that would have the amount of time it takes to get the solution. That sounds good. So that's the idea. And the interior point method allows you to do that. In some problems, that may be faster, but it requires some additional intelligence in the algorithm itself. And so it may or may not be faster, but it has the potential to be faster. There's still research today going on in math departments, computational math departments around the world, coming up with improvements on this basic simplex method, because they're not fast. They work, and they'll give you the solution. But as our optimization problems get bigger and bigger and bigger, we have more design variables and more constraints. Well, we're going to have to wait longer to get the solution. So there's a lot of research going on to improve on these methods. All right, so let me cover the possibilities. So there are various possibilities that can happen. The one that we want to happen is that there is a unique optimal solution that occurs when there's a minimum in J at one of the vertices, in other words, the corners of the feasible space. That's the assumption in the simplex method that we're making. If that assumption is true, then we will get an optimal solution and everything is fine. So this is what we hope happens. That's the possibility that we're hoping for. However, there are some other possibilities as well. What if you were to draw the lines of constant j, what if they were exactly parallel to this line? So it'll still go around from A to B to C, but if it's exactly parallel to this line right here, then C and D will actually have the same j. So that means every point on that line segment between C and D gives the same j. Well, should I make this many x1, x2? Should I make this many x1, x2? Or maybe anywhere, any of these x2s, x1s, x2s along this line segment? They all give the same j. So that is a situation where you actually have an infinity of optimal solutions, because every infinity of points along that line segment between C and D, in that case that I just outlined, would give me the same profit. So on one hand, you say, well, that's not a bad solution because that gives me more flexibility in determining how many of A and B to make to maximize the profit. Maybe there's some other reason to move in one direction or another, but it doesn't, the point is it doesn't give me a unique solution. The third possibility is a big problem. So the third possibility is, what if when I draw my feasible space, it is not a closed polygon or polyhedron? So I have a table and I put my constraints on it, my bumpers on it, but there's a hole. And then my marbles can spill out. So if that happens, my j now could occur at infinity. In this case, minus infinity, because I'm minimizing. Well, that's not an acceptable solution. Don't go to your boss and say our potential profit is infinite. That is not a viable optimal solution. The final possibility is if the constraints are not consistent. In other words, you could have a situation where there are no values of the design variables that are consistent with all the constraints, then there's actually no feasible space or optimal solution at all. And of course, your boss doesn't want to hear that either. So they don't want to hear that there is no optimal solution to the problem. They don't want to hear that the solution is you can make infinite profit. And this is an okay solution, but it gives you some additional choice. This is the scenario that gives you one unique optimal answer. In Python, there is a package built into SciPy Optimize called linprog for linear programming that does this. It has all the options in it that you would want in order to do these kinds of problems. So if you look at the problem set, the very last problem is a simplex problem, and we're solving it by hand. And for extra credit, if you want to try using linprog, or if you want to try to figure out how to do it in MATLAB or Mathematica, whatever you're using, you can try that, and that would be extra credit. So I'm not going to ask you to learn these. I'm not going to require you to know how to learn how to use these, but I want you to know that they are available, that you don't have to program these yourself. And if you're so inclined, by all means, give it a try. And of course, this is problem set 5. So you can do all of problem set 5 now. So I posted it last evening, and it has one simplex problem, which you can now do because we finished that. All the other ones are based on nonlinear programming. So you can work your way through those due on Friday. All right, any questions on optimization before we turn the page to calculus instead of algebra? We're finally going to graduate from algebra to calculus for the rest of the semester. Okay, so, oh, I forgot to upload the notes. I put them on Blackboard. Oh, man. All right, we'll just take a second. I forgot to put them on my iPad. So I sent an email, I don't know, 2 weeks ago, I can't remember how long ago it was. And I said there's a new version of the lecture notes. where I've included another chapter, and I've sandwiched it between chapters 6 and 7 as they occurred in your original notes. And so if you've downloaded the new version, it's the new version of the whole thing, but I haven't changed anything in the old chapter 7, 8, and 9. So it's literally just shift it by one for you, and put the new chapter in. So you can just, you have the new one, new chapter, and that's fine, which is the numerical integration stuff. All right. This is LaTeX. If anybody is using LaTeX, you are way ahead of the game. Most undergraduates don't even know what LaTeX is, and we certainly don't require it. But if you do any kind of mathematical anything in terms of writing, in terms of presentations, LaTeX is the way to go. And I use it for everything, absolutely everything. LaTeX is my life. Yes, LaTeX is awesome. That is correct. Yeah, it can be a real pain sometimes, and it is not easy to learn. That is the biggest problem. If you're going to learn it, you got to really go for it. You can't just kind of half learn it and then decide, am I going to do it? You have to decide, I want to do it because I trust Professor Castle that he knows what he's talking about, and therefore I'm going to do it. I'll put this in my Dropbox. It's hard to talk and do this at the same time at my age. When I was younger, I could do this. Okay. Now, all right, let's go get the new one. What? Are you kidding me? Come on. Oh. Wow. Today is a Murphy's Law day. Everything that can go wrong is going wrong. Oh, here we go. The best thing about LaTeX is the equation editing itself. It's very professional. It's what all journals use. The books that I published have all been written and published using LaTeX. It creates a very, very, very professional result in the end. That's why I use it for everything, because I'm a perfectionist. And so that's why I use it. All right, let's see where we're at here. Oh, I'm not even close. Oh, now we're getting close. Okay, so numerical integration. So this is the new chapter sandwiched. It won't take us too long. Couple classes. It's not difficult. So it's actually kind of nice. We've been working our way up through algebra, linear algebra, nonlinear stuff. Start off with simple. This was the hardest. Optimization was hardest. Now we can kind of go back to 0. And now we're going to do calculus. So everything for the rest of the semester is going to be based on integration and differentiation, differential equations. It's going to be a lot of fun, very interesting, very fascinating, but it will be much simpler, which will make everyone happy. At least we're going to start simple. Things will get complicated quickly enough. This is a relatively short chapter. We're not going to spend a ton of time on this, but we do need to be able to integrate things numerically. Just one example of many that I could give is, let's say we had an airfoil with the flow past it, and I want to calculate the lift and the drag. So, whoops, the lift is the force up on the airfoil, and the drag is the force in the flow direction. So how do we do that? Well, on the surface of the airfoil, if you zoom in on that surface, there are normal forces, which are pressures, and there are tangential forces, which are shear stresses. So at every point along the airfoil, there's going to be a pressure and a shear stress, a pressure and a shear stress. So in order to get the lift, I need to add up all of the pressures around the entire airfoil, all of the shear stresses around the entire airfoil, and take the vertical component of all of those. That's the lift. Likewise for the drag, add up all the pressures and tangential shear stresses all the way around, and I take the horizontal component, and that gives me the drag force. So I'm integrating pressures and wall shear stresses all the way around that surface. How do I integrate? I'm glad you asked, because that's what we're going to show how to do. If these are measured values from an experimental wind tunnel test, then they're just at discrete points. I don't know the pressure at every point. I only know the pressure at the points where I've actually measured it. I only know the wall shear stress at the points where I've actually measured it. Incidentally, this is interesting. One of the best ways to experimentally, we have very different, yeah, sorry about that. I will always put fun in quotes. So interestingly, the most accurate way to measure wall shear stress is the following. So if I have a surface and I have a flow past the surface, that creates a shear stress. So what you do is you put a drop of oil on the surface before you turn the wind tunnel on. Put a drop of oil on the surface. You know the viscosity, you know the properties of it. When you turn on the wind tunnel, that drop is going to look like this. It's going to take a shape like that. You're going to have this flat portion, and the higher the shear stress, the flatter that will be, and the longer your bubble, your little drop of oil will be. So then you can shine a light on this, and you'll get a interference pattern on the surface because of the light going through the oil. And based on that interference pattern, you can determine that angle. And then from that angle, you can determine what is the corresponding shear stress. It sounds kind of archaic, but it's actually one of the most accurate ways to measure shear stress. Because you think, well, how do we measure pressure? Well, we learn how to do that with static tubes, pedostatic tubes, and so forth in our 313 class. That's easy. You just put holes in the surface. You have a little pressure gauge inside, which could be as simple as a tube, a manometer, that you also learn about in 313. And you get the pressure. Super simple, very straightforward. How do you measure a tangential shear stress? You lick your finger and you put it up, right? Well, that's how I do it. Well, that just tells me the direction that the air is going. It doesn't tell me the speed. I mean, colder means faster, I guess, but anyway. So it's actually a very difficult thing to measure. You can't go to Home Depot and order or buy a tangential wall shear stress probe. So that's one of the most accurate ways to do it. It's a very interesting approach. All right. So that's just one of many, many, many examples that we could think of why we need to be able to take discretely measured data along, in this case, airfoil surface, add it up through integration at the discrete points, and then get the total value. All right, so let's just kind of back up. And let's think about for a definite integral. So remember, a definite integral means it has limits of integration. An indefinite integral does not have limits of integration. An indefinite integral is just the opposite of a derivative. A definite integral has the limits of integration. So what that means is we have x, I have my f of x, and then a and b are the limits of integration. So I want to get this area in here. That is capital I. That is the integral. That is the value of the area under the curve between a and b. That is the integral. That's what we're looking for. So I know we're out of time, so I'll stop after this slide. But just to complete the thought here. So you think, well, the easiest, I mean, if you look back in your math class, the definition is of the integral is that the limit as delta x goes to 0 of delta x times the value of f at each xi summed up, that's the value of I. So what that means is you're taking increasingly small slivers, small delta x's, and you're getting these little areas, and you're just adding them up. And the smaller you make delta x, so the more the little slivers you have, the more accurate it gets, until you have an infinite number of slivers between a and b, and then you get the exact value of I. Now, obviously, we can't integrate an infinite number of slivers, so we'll have where delta x is small, but finite. All right, so this is in what you do in your calculus class. Now, we're going to take delta x small, but finite. All right, so we'll come back, talk about that more on Thursday, and go from there. All right, so any questions before we adjourn? Just the move to adjourn. Thank you, you're welcome. Anything else? All right, we'll let them come in and fix this puppy because they're milling about out there, anxious for me to be done. So I will see you on Thursday.